current source that is providing 1 milliamp, and the rest of the elements are simply resistors. So we have R1, R2, R3, 4, 5, and 6. So we have 6 resistors connected to one current source. And what we're asked to do is, let's find the R equivalent seen by the source. So pretty much I'm asked to reduce these combinations of resistors into one equivalent resistor. And then later we're asked to do our find V1, we're asked to find V2, and then we're asked to find I1 and I2 and I3 and I4 and I5 and I6. So all the elements. Basically I'm solving the whole circuit, and I'll be able to know anything I want about this circuit. Alright, so just before I continue, I just want to make sure what V1 in here, because this is a little bit uncommon, or like it's actually commonly used in circuit analysis. That'll become a lot more obvious when we cover nodal analysis. So this particular terminology or this particular notation tells me V1, but typically when we're associating a V, it's associated, there's a plus and there's a minus, there's 2 points. When you see this particular notational convention, you will see somewhere there's actually some sort of a ground in here, or this is basically voltage 0. Remember, voltage is also always referential, so it's a difference between 2 points. So sometimes we assume that the voltage in here is ground or is 0, then we just say, well, this V in here is simply, I'm saying this V is in relation to this particular 0 in here. So what I'm saying is like, how high is this point from this particular point? That's pretty much V1, which is simply stating that the voltage across this resistor R1 is just V1. This is plus, this is minus, and this is just simply V1 in here. All right, the same goes with the V2. So V2 in here, you will see that this is pretty much the plus, and what I'm saying is the minus in here, or you can say the minus in here, it's the same. So what you see is the V2 is the voltage across, for example, the R5 in here. That's what we see. This is the plus, this is the minus. So this notation convention, if you see just V1 and a node and a V2 at a different node, there will be in the circuit somewhere that you will see a reference node or a ground node. That's what we say. Sometimes it is here, sometimes you can put it in here. It doesn't matter where it is, as long as it is somewhere on the circuit, you'll see a ground node in here. Anyhow, moving along now, so we can just start by figuring out what the R equivalent circuit in here. What we will do is I'll identify some of the circuits that are connected in series, some that are connected in parallel. So it's very obvious that these resistors in here, they're drawn in parallel, but if you take a look at it, they share, this is one node that they share, and this is another node that they do share. So R4, 5, and 6 are connected in parallel. And similarly, you will see the R2 and R3 also share this pair of nodes. So they're also connected in parallel. So R2 and R3 are in parallel, R4 and R5 and R6 are also in parallel. And we can read that circuit so that it shows us this particular relationship. All right, so let me just redraw this. You will see that we have a current source in here, and that current source is simply IS is 1 milliamp, okay? And then from here to here, we will see, let me just do this. From here, we'll do that. We'll do this here, and then in here, what we have is we have those kind of resistors, the R1 and R2, or R2 and R3, and then we have another type of resistors in here. So what I've done is this is the I of S, and I know that it's 1 milliamp, and I have one resistor in here, so that basically is V1. This is actually the ground. Sometimes we draw the ground as this way. All right, and what we have in here is R1, that's 70 kilo ohm. This is R1, this is equals 70 kilo ohms. And I think I made a mistake in here. Let me just correct it. So what we have is in here, so let me just do this. This happens when you scroll up and down, okay? So V1, we have just simply R1, and that's basically the 70 kilo ohms. And then what we do is we replace these two R2 and R3 with one resistor. So I'll do that. This is R2 in parallel with R3. And then these resistors in here, we replace them with one resistor. Okay. And that resistor will be here. And that basically is simply R4 in parallel with R5 in parallel with R6. Okay. And we can find out that this point in here, which is this particular node, is still V2. This is here is simply V2 based with the reference. All right, so let's compute these values of R2 and R3. That's simply, if I take a look at it, it's 15 and 30. So it's 15 kilo ohms in parallel with 30 kilo ohms. And if you do the calculation, you'll find out that it's 10 kilo ohms. Okay, and then we can call this here RA, and we can call this one here is RB equals, and this is RA. And that's simply the 4 and the 5 and the 6 is 45, 90, and 60. So it's 45 kilo ohms in parallel with the 90 kilo ohms in parallel with the 60 kilo ohms. And if you do the calculation here, you'll realize that this is simply 20 kilo ohms. Okay, I'll just highlight it so that we figure out this. So this is RA, and this one here is RB. Okay, this one here and this one here. All right. So now, obviously, we have those V2 and V1 are still the same. We have R1, so we're not done. We're looking for the R equivalent that is seen by this source. Well, hopefully by now you'll see that the RA and RB basically share one node, not pair node. So RA and RB are simply in series, so we can combine the 10 and the 20 to become 30. And then we can combine these two in here in parallel with the 70 here. And I can redraw the whole thing in one shot. For example, this is 1 milliamp, IS equals 1 milliamp. Okay, and it is just simply connected to one R equivalent, and this R equivalent is simply, it's RA plus RB, and the whole thing is in parallel with the R1, and that simply is 10 kilo ohms plus 20 kilo ohms in parallel with simply 70 kilo ohms. And the answer is going to be 21 kilo ohms. This is the resistor seen by this particular current source. So this current source in here that is providing 1 milliamp is just connected simply one resistor 21 kilo ohms, or you can replace it with that. And of course, we're still in here, we're still having V1, because what I did is I combined these two. Of course, V2 will disappear because I combined them, it's in the middle, and then while V1 is the same in here and is the same in here, so it is the same combination in here. So what I have in here is I can just say that this is V1 and this is basically my ground. And the V1 obviously is the same voltage across that resistor or that source in here. So we can compute that V1. So we can, if we compute the V1, we can easily just figure out what the power dissipated by that source and so forth. But what we're asked to do is we're asked to compute the following. We're asked to compute what V1 is, what V2 is, and then we're asked to compute the different current within the circuit. So I'll start by saying, you know what, I think I can figure out what V1 is right away from here, and it's simply using Ohm's law. So Ohm's law tells me that V1 is simply the R equivalent times I, okay? And I know that it's simply I of S in this particular case because the current is actually just simply flowing this way. And if I assume that this is plus, this is minus, it tells me that the voltage or the current is hitting the positive, so I should be seeing a positive in here. So that's simply 21 times 1, which is just simply 21 volts. Of course, there's a kilo ohms and a milliamp, so they go together, so that's simply 21 volts. That's V1. So I can say that V1 is just simply 21 volts. Okay, and this V1 in here is just simply 21 volts. I'm just writing this in here. All right, so of course, now we can figure out the I1 if you think about it, because I know the voltage between here and here, and I know the resistor, I can figure out what I1 is, and I1 is just simply an implementation of Ohm's law. So I1 in here, I'm just gonna write it. So I1 is just simply V divided by R, or V1 divided by R1, which is just simply 21 divided by, what's the value of R1? It's 70 kilo ohms. Which is, this is of course 70 kilo ohms, which is simply 0.3 milliamps. Okay, so we know what I1 is now. We can, I'll just write this in here. This I1 is just simply 0.3 milliamp. Okay, do we have I1 anywhere here? Yes, we see I1 in here. This is I1. This is just simply 0.3 milliamp. Okay, of course we can figure out what the R going that way if we know it, because I know the current going here is IS and I1, so I'll call it IAB. Okay, because it's going to these two resistors, which are A and B. I'm just going to call it that way, and I'll just highlight it in here as well. Let me just change the color so we can track it. So we can just say that this here is simply IAB. Okay, so here it's the same as this one in here. So this is I, A, and B. Okay, it's not R2, it's not R4. It's actually because the I of S gets split into I1 and IAB, because these I replace them with RA and RB. Okay, so let's try to figure out what IAB is simply we can write KCL in here. KCL tells me I have 1 milliamp coming in and I have 0.3, so that must be 0.7 milliamp. Like I can write it, but it's really straightforward. So IAB is just simply I of S minus I1, which is 1 minus 0.3, which is just simply 0.7 milliamp. Okay, I can write that 0.7 milliamp in here. That is here is 0.7 milliamp. Okay, and that here is just simply 0.7 milliamp. Okay, well, that's good. Now, what can we tell? Well, we can figure out now what we have is we have this current is actually going through RA, and it's also the same current going through RB. And if I know what RB is, which I do, I know it's 20 kilo ohm, I can figure out what the voltage V2 is using Ohm's law. So let's figure out what V2 is. So V2 is simply IAB times RB. So let me just double check. We have assumed that this is plus, this is minus, and we have this I of AB going to the positive times R of B. Okay, so that's simply IAB is 0.7 times RAB. Well, we figured out the RAB is just here, which is 20 kilo ohms. Okay, so that's times 20 kilo ohms. Okay, so that tells me that this here is 14 volts. Okay, so we know that V2 is 14 volts. So this one here, V2 is simply 14 volts. Okay, and we can write this here is simply 14 volts. Okay, all right. So that's good. Now, can we figure out the I4? I believe we can figure out now that I know that the V2, which is the same voltage across the R4, the R5, and the R6, so I can technically figure out what I4, I5, and 6 is. So that leaves me with I2 and I3. Well, why don't we just do that? We'll do R4, R5, and R6, and then we'll come back and figure out how to figure out I2 and I3. Okay, so I4 is just simply V2 divided by R4. And then I5 is simply V2 divided by R5, and then I6 is simply V2 divided by R6. So let me write these out. So I went ahead and I computed all of these. So I4, and I just simply took the V2 that we got and divided by R4, V2, and divided by R5 and R6. And of course, the R4, 5, 6 are 45, 90, and 60 kilo ohms. So they're 45, 90, and 60 kilo ohms, and these are the actual values that we got. So I know the value for I4, I know the value for I5, and I know the value for I6. Okay, so now we computed pretty much everything except for I2 and I3, and there's multiple ways we can do this. And I think the simplest is if we can figure out the voltage between here and here. So let me just highlight this in pink. If we know what the voltage in here, and let me call it V. Well, let me just do it that way. So it's some sort of a voltage in here, and that V is between here and here, if I can figure out that. And if you think about it, this particular node in here is simply V1, and this particular voltage in here is V2. So what I'm trying to see is a voltage difference between 2 points that I know what the voltage is. I know that this is V1, and I know that this is V2. So simply what I'm really asking is, this has to be, well, it's V1. And now that we know the voltage across this R2 and R3, it's straightforward to compute what the current I2 and I3 is. So simply I2 and I3, I can write I2 is equal and I3 is equal. It's just simply this VA, and this is VA divided by R2, and this is divided by R3. And of course, just to double check passive sign convention tells me this positive is hitting the positive, this current is hitting the positive. So that's divided by 15, and this is 30. Okay, so this is 15 and this is 30. Okay, so that's here is simply, believe it is 7 divided by 15, and this is 7 divided by 30. And this here is milliamp, and this one here is in milliamp. And you can double check the answers by combining. For example, we know what IAB is, and we know it splits to I2 and I3. So if you combine I2 and I3, let's combine them. I should get 0.77. So let's combine these two. And you will see that the answer is simply 0.7 milliamp, which makes sense based on KCL. The 0.7 milliamp, it splits, and then they get merged again. And they get merged again, and you can figure out also, like if you sum up I4, I5, and I6, they should also be the same. All right, because if you write the KCL in here, you'll see the I4, I5, and I6, they become here IAB, which splits back into actually I1 in here, and then the I source in here.